Okay, so today we are going to be starting off with a bit of a review. Okay, talking a little bit about waves. And so that's going to lead us into a discussion talking about sound waves and light waves. Okay, now there are two different types of waves that we are going to talk about in our context of today's discussion. Something called a longitudinal wave and a transverse wave. Okay, these waves, the way in which they are set up, the way in which they propagate, which is a fancy term for just talking about how that wave is going to move. Okay. Sound waves are going to propagate as a longitudinal wave. Well, what is a longitudinal wave? Well, it's not one that has the traditional rise and fall and come back to a rest position that you might think of as a traditional wave. It travels as a series of compressions of particulate matter. And something that I know you probably haven't heard of before is a rarefaction, which is the part in between the compressions of the particulate matter. Now, obviously right now I'm speaking, and I'm pretty sure most of you are at least listening to what I have to say. How does the sound get from me to you? Well, yeah, a wave, okay. We get that part of it, but let's be maybe a little bit more specific. And yes, we know it is a longitudinal wave now, but what's actually happening with the particulate matter between me and you? And my voice is creating vibrations in the air, where it's compressing that matter. Then again, we have obviously the space in between those compressions. Okay? As those compressions are made, the energy that they have travel through some sort of medium. Okay? In this case, it's all the particulate matter we have in the air. Do sound waves travel through space? No. Because the particulate matter, there's very, 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 very little particulate matter is there. There's no way for that to kind of transmit the energy along. Okay? Can we send sound waves through something else other than air? Absolutely. Can we do so through water? Absolutely. Can we do so through solid objects? Yeah, it's possible, okay, depending on the intensity of that sound. But we just need some sort of particulate matter. So we have those particulate matter that just kind of bunches up in these compressions. That energy is transmitted through that medium to you. Okay, right now in terms of listening to what I have to say. Now that's because in your ear you have small little bones and a fluid that helps you pick up on what that vibration is and translate that into a signal that your brain can process. Okay? So the point though about the wave itself is that we have to have that particulate matter that's there. All longitudinal waves require a medium in order to travel through. Without it, it simply doesn't happen. Now sound, as it travels through air, travels so at an average speed of about 343 meters per second. Okay, which if we translate that to US of A speed, that's about 700 miles an hour. Okay, is that a pretty fast speed of travel? Absolutely. Okay. But do understand that that could vary. And I'll throw it out to you. If we're talking about, guys, that the average is 343 meters per second, what are some factors that you believe could influence the speed at which that travels? Altitude, absolutely. Okay, we go up to a very high altitude. Certainly, the air is not as dense. Okay, it's a little bit particulate matter, a little bit more spread out due to the altitude. Or if we go to a very low point, okay, it's going to be more dense as a result of that. Okay, so altitude is one factor. For right now, though, because most examples are probably going to be right about here, let's just assume we're at or about sea level. So it'll be pretty consistent. There still are some other things that could affect it, but altitude absolutely is one. Humidity. Okay, think of a day like today. Okay, we had rain last night. Okay, it's a little bit hot and humid outside. Certainly, all that moisture in the air adds to the particulate matter as to what's there. So that makes it a little bit more dense. Okay, anything else? Absolutely. And those are the three we're pretty much looking for. Okay, so the temperature certainly makes a difference. Okay, when it is hot outside, and let's take the humidity factor out of it, just based on temperature, is the air more dense or less dense? Less dense, spreading out a little bit more as a result of that. So on a cooler day, very cold day, that air is actually going to be a lot more dense at that time. Okay, so those are all factors. Now, are there other things that can impact it to a smaller extent? Yes, but those are pretty much the most common ones that we can chat about. Now, electromagnetic waves, which visible light is just one part of the electromagnetic spectrum, can travel as, or it does travel as, a transverse wave. Now, at first, the definition of a transverse wave might not necessarily seem to make a whole lot of sense, but it is true. Okay? Transverse waves have particles that move perpendicular to the direction of the way the wave is traveling. Okay? So, let me kind of give you a little bit of a conceptual example of a transverse wave, not light, but something else. Okay? Let's imagine for a second that I have a rope, as we're standing on this side of the room, and that rope is tied to a doorknob on the other side of the room. We're going to go ahead and we want to send a transverse wave through that rope. So what do? I take the rope from its rest position, lift it up, all the way down, and then back up to rest position. Now certainly you can envision the energy going along that rope, and you're going to see the wave travel across that rope as it travels across the room. So the wave is traveling in that direction, but the question that I pose to you is, what direction does the rope actually move? It just moves up and down. So the particulate matter is not actually traveling from where I'm standing to the door. For the most part, that's just traveling up and down. Again, it is the energy that is transmitted along that wave. That's what's important. So that's kind of that example with a rope. But these transverse waves, okay, what do we have? Okay, light and other transverse waves, they do not require a medium to travel, which is a good thing for us here on Earth. Light and the heat energy we would get from that required a medium to travel through? Well, it would be. So let's talk about a couple of wave properties. Okay, things about the wave that we need to do. If you could do me a favor, if you haven't done so already, please don't start labeling this just yet. There's actually one thing, not that it's wrong, but one thing that I like to represent a little differently. Okay, so parts of the wave. Certainly, we would have the crest of the wave. Where is the crest of the wave going to be? Topmost point of this transverse wave. We can label the crest, and your diagram in your notes, we have a couple different spots we can make that. That's fine. But it would be the topmost point of the wave. The counterpart to the crest would be the trough. Okay? That is going to be the bottommost point of the wave. Now here's what I like to label a little bit differently than what's up here on the board. I believe it would be a good practice if we are going to measure something called the wavelength, which, get this, is the length of a wave. Okay. I prefer to measure that from crest to crest or from trough to trough. The way it's drawn on the board is not technically wrong, but it might be a little misleading depending on how we are presented with the information. Now, I know, yes, the textbook definition of wavelength is the length of a wave, but how specifically are we going to measure that? We are measuring repeating points on the wave, and it must go through one entire cycle. So, if we were to start here, sure, it would go up the crest, then all the way back down to the trough, then back up to the rest position over here. That would be the same length as what it would be crest to crest or from trough to trough. But where some people might make the mistake, and this is wrong, I'll mark it with an X, is they might only measure from the dot to the X and call that a wavelength. It has not gone through one complete cycle. So if you go crest to crest or trough to trough, it makes it a lot easier. Assuming that you know those things. Okay, the last one that we need to talk about is amplitude, which is simply the distance from rest position to the crest or from rest position down to the trough. That's the amplitude. From rest position up to the crest or rest position down to the trough. Now, hopefully these terms are not anything that's new to you. But set the stage for some of the things that we're going to chat about on our next slide. So, quick check for understanding. If an explosion of some kind were to occur in another place in our solar system, would we see it, hear it, or both? We would be able to see it. We would not be able to hear it. Because when we're talking about space, okay, for the most part, the complete lack of particulate matter, okay, there's no way to transmit the sound energy alone. It does not have that medium to travel. And the wave's speed, sometimes it's represented as the velocity of the wave. The wave's speed is directly related to its wavelength and frequency. Now, for wavelength, we use the variable lambda, which is kind of like an upside down y. It is the distance between repeating points of the wave, as we just chatted about. And since it is a length, we will use the SI unit of the meter in order to measure it. As long as we know two repeating points of the wave, measure the length between those 2 points, that is our wavelength. I don't think that's incredibly complex. Frequency is a measure of the number of waves passing a given point per second. The SI unit for frequency is expressed as the hertz, capital H, lowercase c. And if we kind of take a step away from the science side of it, you already know what frequency is. How frequently do you do something? It's how many times that event occurs per unit time. Okay, here we're measuring the amount of waves that occur passing this point per second. Okay, and that is expressed in hertz. So the wave speed equation, well, if we're trying to find the velocity of the wave, okay, it is simply going to be our wavelength times our frequency. One more, and this is actually a term that we used way back in January. Period. Period, represented as a capital T, is a measure of the amount of time for one wave to pass a given point, and can be found by taking the inverse of the frequency. Now, anybody remember where we've seen period before? What unit we were talking about or anything? It was related to centrifugal force in that unit. It was uniform circular motion. Okay? So in circular motion, we talked about that, and period was the amount of time for one revolution, one cycle to go around. It's the same concept here, except there's the amount of time for one full wave to pass a given point. We're still going through one cycle of that wave, but that's what that period is going to measure. It doesn't directly state it here, but what units do you think we're going to use for periods, just like we did before? Let's go back to its definition. It is the amount of time for one full wave to pass a given point. Seconds. Okay? We'll express it in seconds. So it's almost like you're taking a stopwatch and you're starting it. All right, see how long it takes for that wave to pass a given point. Just one wave. Never stop. Okay. Frequency is the inverse of that. Think about the definition. Okay. Frequency is number of cycles in 1 second. Now, for a period, it is how long it takes one wave to pass a given point. So, the bottom of your note page, okay, we have a couple of waves that are drawn there, and a couple of questions to follow. Which wave has the greatest wavelength? What do we all say? Should be A. Because if we go crest to crest or trough to trough, it certainly should be A. And I think you can also see here that rest position is not drawn in, so it would be harder to determine a wavelength if we're trying to use that as a point to measure. Which one can have the greatest frequency? Assuming that all of these waves are produced in the same amount of time, which let's just say would be in 1 second, these are the waves that are produced, it certainly should be E. That gives us the most amount of waves per second. That's going to be the greatest frequency. Which one has the greatest period? What is period? It would be the amount of time to go through one complete cycle. So what's going to take the greatest amount of time to go through one complete cycle? A. Absolutely. Okay. Kind of giving you a little bit in terms of notes. Any questions on anything so far? Most of this in review, even if it's been a long time since you've thought about some of this sort of stuff, some of it at least sounds familiar? Good. Question? Okay. Electromagnetic waves. It is worth saying that all electromagnetic waves travel at the exact same speed through a vacuum, meaning that there is no particular matter that would slow it down. That is more than just visible light. The entire electromagnetic spectrum will travel at 3 times 10 to the 8th meters per second through a place like space where there is no resistance to its motion. Now, it is worth noting, it really is 2.99 followed by a whole bunch of other goodness times 10 to the 8th meters per second. But as sometimes it's done with this sort of stuff, unless we're getting very, very specific on things, a lot of physics land will abbreviate that into 3 times 10 to the 8th meters per second. Okay. Now, to put that in context, we said sound travels at 343 meters per second. And now we're talking about something that's traveling at 300 million meters per second. There'd be quite a bit of difference in terms of those two speeds. Not that sound is necessarily slow, but light traveling through a vacuum is the fastest thing in our universe, and will always be the fastest thing in our universe. Now, the reason why we call it an electromagnetic wave, because as these waves propagate, they actually create an oscillation or a change in an electric field as it travels, as well as a magnetic field. So they're two separate things, but it does create a change in the electric field and magnetic field as it propagates. It is worth noting that I would love to go into more detail on that. We just don't have enough time for this in our crash course one day of electromagnetic waves and all the other good things that come with it. Electromagnetic waves do not require a medium to travel through, as we talked about earlier. And typically electromagnetic waves have very, very small wavelengths, to the tune of, we usually express their wavelength in nanometers. How do we express a nanometer? It's whatever it is, times 10 to the negative 9th meters. And we have seen micro before. We saw that a lot in electrostatics. Micro is times 10 to the negative 6th. Okay? And nano is times 10 to the negative 9th. I just want you to be aware that a lot of those wavelengths can be expressed as that. So, yes, go. Also, in terms of the abbreviation for nanometers, a lot of times we just see lowercase n, m. So just so when you get to that, notation-wise, you'll see that information. All right, so just real quick, and again, I wish that I could do a lot more in talking with the electromagnetic spectrum, but do understand everything that's up here on the electromagnetic spectrum that you see, including this very small band in the middle that is visible light, which is your red, orange, yellow, green, blue, indigo, violet. That's a very small part of it, including radio waves, microwaves, infrared rays, ultraviolet, X-rays, and gamma rays. And all are electromagnetic waves. To reiterate a point, we know the speed that all of them travel. Do that. They all travel at that 3 times 10 to the 8th meters per second. Now, there's a question down here at the bottom, and that is probably related to something that, dare I say, is almost antiquated at this point. But does anybody even know what AM and FM stand for the radio station? Not with this. Good guess. You're absolutely right. Okay? That the AM stands for amplitude modulation, meaning that the way that the signal is sent is through altering the amplitude of that wave. Okay? And that with FM is modifying the frequency of the wave itself. Now, there are benefits and drawbacks to both of them. That's different from getting your satellite radio or something else. Okay, with an AM radio signal, typically with only altering the amplitude, those are able to travel much longer distances. Okay, they're actually able to kind of go around some larger objects like mountains and things like that. It's not unheard of that you could be potentially, 100 miles plus away from a radio source that is an AM signal and still get a crystal clear signal because it's able to travel longer distances without getting as much interruption to the signal itself. Whereas FM, it doesn't travel as far. But there's a benefit to FM, and there's a reason why most FM radio stations are music stations. Because the FM signal is much better sound quality to get out of that because you are modulating the frequency. What is music? We're talking about frequency, being able to have that clear sound. That's what FM is good at. And AM typically are more of your, kind of talk shows and that sort of stuff. That people even listen to radio anymore in that traditional sense. But anyway, kind of fun little fact for you. So, would AM or FM radio waves bend more readily? Now that I've pretty much given you the answer, the AM radio waves. They're able to kind of travel longer distance and be able to move around things a little bit easier. If that be the case. All right, if you can, I know that there's a little bit more space in your notes, but for right now, we're going to stop here. If we can, please take out the wave practice problems that you picked up on the way in. And I'm just going to ask to take a little bit of time, and I would like for you to please go ahead and complete problems 1 and 2. 1 and 2. Okay, so now checking in on 1 and 2. Responses up on the board, hopefully. Exactly what you have written down as well. Okay, it is worth noting, just like the wavelength, the amplitude should be expressed in meters. Because 7.5 centimeters, I'm going to express that in meters. So we do a decimal point 2 places to the. So as we go from 7.5, 2 places left, we make that 0.075 meters. Hopefully, I think you're finding number 1 pretty straightforward. Okay. And number 2, there's never a whole lot of complications to it, but you were not given the period like you were. I'm sorry, you were not given the frequency, you were given the period. And so in order to find that, just remember, we just have to rearrange that period equation to solve for the frequency. And then once we have wavelength and frequency, we should be able to figure out wave speed pretty easily. Okay, any questions on these? I know that the math, hopefully, pretty straightforward. And we've got our units together. Any questions? All right, good stuff.